This is the last of 3 lectures from Chapter 17, and this lecture will focus on what we call KSP, which is solubility product equilibrium constant. It turns out that all ionic compounds have some measurable degree of solubility in water. Now, in the first semester of chemistry, you were taught that there were some insoluble ionic compounds. And what it turns out is those compounds have such low solubility that it can essentially be neglected in most cases. But there is a measurable, although very, very small, solubility, and that's what this lecture is about. As with anything that's soluble in water, solubility in general is in equilibrium at the saturation point. So if you put a solid in water, it's going to start, as it dissolves, it's going to separate into, if it's ionic, into the cations and anions, and then once the solution reaches the saturation point for that substance, the reverse reaction will begin to occur. The ions will recombine to form the original intact ionic solid, and equilibrium is reached, as always, when the rate of the forward process equals the rate of the reverse process. And so the equilibrium we talk about in this lecture, KSP, refers to the solubility equilibria. So just kind of to visualize what's going on, as I said in the last slide, in the beginning, when you put a solid ionic substance in water, it's going to start dissolving in the individual ions. The cations and anions are going to be escaping into the aqueous solution, being solvated by water molecules. And at some point, when you build up enough solvated ions, some of them are going to begin to recombine and what we say precipitate. Okay, that means a substance coming out of solution to reform the solid substance. So eventually at equilibrium, this dissolving process and the precipitation process, the rate of each will equal one another. These two things will equal one another, and equilibrium will have been achieved. So as with any equilibrium, if you're going to do calculations, one of the first things you need to do is set up the expression for equilibrium. KSP is a little bit unique. So if you look, for example, at the dissolution of silver chloride, and you write an equilibrium constant expression for that dissolution, you get this. Now, one thing I may need to remind you is that if you're writing equilibrium expressions, you do not include pure solids and liquids in the expression because they have a constant concentration. It does not change. It's not variable. And so it's just its value is kind of lumped in with the constant, equilibrium constant. In any case, with all KSPs, the reactant side, the substance on the left side of the arrow, will always be a solid. And so you will never see KSPs having a denominator because of that. So all of the equilibrium expressions for KSP will only have numerators. Alrighty, so to get an idea of what some of these KSP expressions look like, look at these 3 sample solubility equilibrium equations, and all of them are slightly soluble salts. The salts or ionic compounds that we consider extremely soluble or virtually completely soluble would not be associated with equilibrium values. Just like a strong acid and strong base are not associated with Ka and Kb values because it just wouldn't make sense. The equilibrium lies almost totally to the right for these substances. So again, these KSPs are only for the slightly soluble salts. Just as a reminder, as with any equilibrium expression, the coefficients become exponents in the equilibrium expression, and that's Don't forget those, okay? So make sure you could write these KSP expressions for all sorts of slightly soluble salts. And notice again, none of them have a denominator. As with all equilibrium constants, the greater the value of KSP, the more soluble the salt or the ionic compound is. Just to give you an idea of the KSP values for various slightly soluble salts, some of them, and none of them here are really small. I suppose -29 is pretty small. But you'll actually see some KSP values that are like 10 to the -70. I don't even know how they measure that small amount of solubility. But they tend to be quite small in general. All right, one of the most common misconceptions when learning about KSP is getting KSP confused with what we call molar solubility. Solubility is a concentration, okay? So if a problem is saying, what is the solubility of something, they're asking you for the concentration. They're asking you for the moles per liter of a substance, okay? So if I were you, I'd write that down and highlight that right now. Solubility means concentration of something, okay? Now, solubility product, which is what some people call KSP, is a combination of multiplying solubilities, right? And sometimes raised to some power. Okay, so solubility product is KSP. Solubility by itself is a concentration of one specific substance. All right, so let's look at some sample type problems that you will be expected to be able to do with KSP. This one is talking about copper 1 bromide. So if you've gotten rusty on writing formulas from names or vice versa for ionic compounds, you'll want to brush up on that. If there's a number in Roman numerals, that means you're dealing with a transition metal. And that number tells you the charge on the transition metal. So this is copper with a 1 charge. And then hopefully you remembered the charges that other standard elements have when they're ions. Bromine is a halogen. They all have a charge of -1 when they become ions. Then if you crisscross these charges, the formula of copper 1 bromide is simply CuBr. So as with any problem, you want to write out the chemical equation that represents what's going on. So here is the equilibrium of dissolution of copper 1 bromide. This is a simple one because the stoichiometry is 1 to 1 to 1, but we're going to start with something simple. The problem asks you to calculate the KSP value. And so obviously you want to set up the expression for KSP based on the equation. And now as with any equilibrium, you need to go ahead and set up your ice table. In this case, the problem gave us the solubility. Now, what's the key here is remembering what solubility is. Solubility is concentration. So they're giving you the solubility of copper 1 bromide. So they're saying the concentration of copper 1 bromide equals 2 times 10 to the -4. Okay? Now, so what, you might say? Copper bromide solid isn't important in the ice table because it's a solid. Well, if they give you the solubility of any of the substances, through stoichiometry you can figure out the solubility of all the others. So 1 copper bromide, when it dissolves in water, makes 1 copper ion and 1 bromide ion. Okay, so if the solubility or the amount of copper bromide 1 that dissolved is this, that means that the concentration of copper ion is also this, and the concentration of bromide ion is also that because of the stoichiometry. So here we go. we start with 0 amount of the salivated ions, and we know based on what the problem told us that the amount of each of those salivated ions we form is 2 times 10 to the minus 4. So it's pretty simple. Now we know the equilibrium concentrations, which we then plug into the expression for KSP. KSP value for copper 1 bromide is 4 times 10 to the minus 8. That is a pretty simple one. All right, here's another one that is going to have some stoichiometry involved. It's not all one-to-one. And so these are the things I want you to try to do on your own now. I want you to go ahead and write the equilibrium chemical equation showing the dissolving of bismuth sulfide. And that just means breaking it apart into the cations and anions and making sure that the equation is balanced, your coefficients are correct. And then go ahead and set up an ice table. See if you can fill in the values in the ice table, paying special attention to the coefficients. Okay, you're going to, there. And then write out the expression for KSP. See how far you can get on your own. Put the video on pause. And then on the next page, I'll show you how to go about this slightly more complicated problem. Alrighty, so as always, especially on a free response problem where you want to show your work, you want to write out the equilibrium equation. Now notice here that subscripts become coefficients. This 2 tells us there are 2 bismuth in each unit. And so when it separates, you're going to get 2 bismuth and you're going to get 3 sulfide. Now make sure, since anytime you have KSPs, you're breaking apart into ions. Ions have charges. You must show the charge on each. Now, if you don't have a transition metal, you can just go to the periodic table. See, sulfur is in the oxygen table, and we know that when they become ions, they have a charge of -2. So make sure you get the charges correct. If you're panicked on a test and you just quickly want to take an educated guess, you can reverse crisscross. In other words, this 3 subscript becomes the charge on bismuth. This 2 subscript becomes the charge on sulfur. Okay, so in any case, the stoichiometry that we have now tells us that for every 1 bismuth sulfide unit we dissolve, we're going to end up with 2 bismuth ions and 3 sulfide ions. So this stoichiometry is important for the change row in the ice table. Stoichiometry always corresponds to that middle row in an ice table. All right, so down to setting up the ice table. I noticed that it looks like I forgot to write the amounts here. So let's see. This would be bismuth above this column. And this would be sulfide, okay, above this column. Okay. And of course the bismuth sulfide, because it's a solid, you don't even really have to show it in the ice table, but if you do, there's just a big X. Okay, so as always, we're starting with the initial amounts of the ions is 0. The problem told us that the solubility, the concentration of bismuth sulfide that dissolves, is 1 times 10 to the minus 15. So that they're essentially telling you what X is. Okay, solubility is typically the X in your ice table. So if you want the change for the bismuth ion, remember this coefficient of 2 comes down here, and coefficient of 3 comes in under the sulfide. Okay, so if we just carry out that math, we get the equilibrium concentrations of each of the ion. And once you have equilibrium concentrations, you're essentially done. Now all you're going to do is plug into the expression for KSP. So here's the expression for KSP. Now listen really carefully, because this throws a lot of students off. The expression for KSP, of course, has exponents because of stoichiometry. And do not forget those exponents when you're plugging in the equilibrium concentrations. You're going to feel like you accounted for this coefficient of 2 and coefficient of 3 twice, but this is the correct way to do it. So the equilibrium concentration of bismuth, plug it in, and then don't forget to also include your exponent of 2. Okay, so even though you doubled the concentration of bismuth, you also have to square it. So you are going to feel like you're doing things 2 times, but this is the correct way to do it. The concentration of sulfide ion is 3 times 10 to the minus 15, but then you also must remember to cube it. Okay, so there's a lot of math, although simple math going on, and check out this KSP value. 1.1 times 10 to the minus 73. So that means bismuth sulfide has an almost inconceivably low solubility in water. All right, here's one for you. If you didn't try the last one on your own, well, regardless, try this one on your own. This should not be really hard. It has a little bit of stoichiometry because it's got this 2 here, but not as complex as the one we just did. So turn off the video, give it a shot on your own. And remember, you always want to start by writing the equation to show how lead 2 bromide dissolves. And then you want to write the KSP expression. Okay. And then you want to draw or set up your ice table. Okay, those are the generic steps. Okie doke. So here is the reaction equation for dissolving of lead 2 bromide. I've started to set up the ice table. I'm going to write the KSP expression down here. And I'm going to be sure that I include any exponents that I'm supposed to. There's a 2 here. And I'm going to make a little note to myself that if I call the amount of lead 2 bromide that dissolves X, then the solubility of the lead cation would also be X because it's 1-to-1 stoichiometry. But the quantity of bromide, the solubility of bromide, would be 2X. And so the problem gave me the solubility, the amount or concentration of lead 2 bromide that dissolved. And that amount was 0.00217. I'm going to think of that as X. And so the change or the concentration of lead ion that forms would also be 0.00217, and the amount of bromide ion that forms would be 2 times 0.00217. And so if I multiply that correctly, I get that the equilibrium concentration of bromide ion and the equilibrium concentration of lead ion. Now I can plug into the expression for KSP, being very careful to not forget the superscript. So 0.00217 times 0.00434 squared. And so your final answer here would be 4.09 times 10 to the 36 minus 8. That would be the KSP value, which was C on the original question. So this sample problem is a little bit of a twist on the few that we just did. This problem is asking you to solve for, whoopsie daisy, this problem is asking you to solve for solubility, and it gives you KSP. So if you remember the other problems we just worked, they gave you solubility and asked you to solve for KSP. So what I want you to make a note of, and that once you understand that, it'll make the problem a lot easier. If you are asked to solve for solubility, they're essentially asking you to solve for X. Remember, solubility is a concentration. So your goal, if they ask for solubility, is to solve for X from the ice table. So let's work through this one. As always, let's go ahead and write the dissolution equilibrium for zinc 2 hydroxide, and pay attention to your stoichiometry as always. Set up your KSP expression, don't forget any exponents, and then go ahead and set up your ice table. Now, if we call the concentration of zinc cation X, of course, then the concentration of hydroxide ion would be 2X. And so now plugging into the KSP expression, concentration of zinc would be X, concentration of hydroxide would be 2X squared. Okay, now here's another very common error. When you 2X squared equals 4X squared. A lot of students tend to just square the X and forget about squaring the 2. So when you complete the math on this KSP value, you get 4x cubed. 4x cubed is the most common expression you will get when you're solving KSP problems, 4x cubed. So if you find yourself with something like 2x squared or 4x squared or something, you probably made a math error and it's worth just checking your work. Okay, now to simplify 4x cubed, you set all this equal to KSP. The first thing you want to do is divide both sides by 4. Okay? Once you do that, you want to take the cube root of both sides. Check the calculator that you're going to be using for the exam. It may not have a cube root function. So I want to remind you that taking the cube root of something is the exact same thing as raising something to the 1/3 power. Okay, so right now I would get out the calculator you're going to use for the exam and make sure that you have a way of taking a cube root, because that's going to happen frequently with KSP problems. So here's one for you to try. It's another one where the problem gives you the KSP value and asks you to solve for solubility. So go ahead and turn off the video and see how you do that on your own. This style problem is the one that's most commonly missed, so I encourage you strongly to try this on your own. All right, so I've written out the dissolution KSP equilibrium for dissolving aluminum phosphate. And this one should be relatively easy. I hope you could do it because stoichiometry is just 1-to-1. So for every X amount of aluminum cation that's formed, we're going to get the same concentration of phosphate ion formed. All right, and so the KSP expression is simply concentration of the aluminum ion times concentration of phosphate ion, no exponents. So now I just have X squared, and I set that equal to the given KSP value, and that was 9.83 times 10 to the minus 21 equals X squared. Take the square root of both sides, and X, which is the solubility, or the amount of aluminum phosphate that dissolved, equals, let's see, 9.91 times 10 to the, let's see, 3, 6, 9, 11. Okay, very small as usual. Now, X again, that's the amount of aluminum phosphate that is dissolved. How do I know that? Because what I assign to X, they all have stoichiometric, the same coefficients, 1-to-1-to-1. All right, so there are a couple of other kind of side notes on KSP that I want to go over, but we're getting closer to the end. And there is something called a common ion when you're dealing with KSPs that affects solubility. And so it also is related to Le Chatelier's principle. So let's first of all think about the equilibrium that's involved in dissolving a slightly soluble salt such as lead 2 chloride. Let's assume that you're at equilibrium, and so the rate of dissolving is equal to the rate of precipitation, reform of the solid. And let's say that after that equilibrium, we dump in a common ion. Let's just say we dump in table salt, sodium chloride. Well, that's immediately going to dissolve into and dissociate into the individual ions, sodium and chloride. And that's a problem because the chloride ion is going to affect the solubility of lead chloride. It is a common ion, and so by essentially adding more of the product, if you think of Le Chatelier, what happens when you add more product? Le Chatelier says equilibrium will shift left toward reactant to get rid of that extra product. And so if you're talking about KSPs, if you shift left, what happens? That means you form more of the precipitate. Now, just to remind you, precipitate, the definition of that is formation of an insoluble solid. Okay, so if you see a solid forming out of a solution, that is a precipitate. And that's what would happen if you add more of one of the ions. Here is an example that involves a common ion. These are a little trickier. So if I know you had this in your KSP lab. I know you had to work through this. I'm not sure how much of it you understood when you were working through it, but you did one. It might be a good one for me to put on as a bonus, but I don't think I would put it on as just a standard question. So here's a sample problem. What is the solubility of silver iodide if you already have a 0.274 molar solution of sodium iodide? So hopefully right away you can, by reading this, see you have a common ion. You have iodide in both of them. So you can only set up the equilibrium of the substance that is slightly soluble, or the substance you were taught earlier is actually insoluble. I'm hoping that you remember that any ionic compound with a group 1 metal, such as sodium, is totally soluble. If you have totally soluble ionic compounds, they're not going to establish an equilibrium. It's going to be a one-way road, okay? You're going to put it in water, and it's going to 100% dissociate into the cation and anion. You're going to have none of the original undissolved salt present, kind of like a strong acid, strong base. So now you have 0.274 molar as the concentration of iodide ion already present from the sodium iodide. And then you put in silver iodide, which is a slightly soluble. Previous you were taught that it's insoluble. But here we go. So we can set up a KSP expression for the slightly soluble material. It's going to dissociate the one part of it that does dissolve into its cation and anion. And we're going to set up an ice table to figure out how much of these we have. But in the back of your mind, you're going to realize, wait a minute, less of this is going to form because I've already loaded the solution up with iodide from the sodium iodide. So let's see how we handle that in an ice table. All right, so the initial amount of silver ion, just as always, is 0. However, the initial amount of the iodide ion is not 0 because we have this presence from dumping in the sodium iodide. So the initial amount of iodide is actually 0.274 molar. The extra amount of silver and iodide ions that we're going to get from dissolving silver iodide are X and X. There's a 1-to-1 stoichiometry. So the equilibrium concentration of each of these, okay, so for silver is going to be X. For the iodine ion, the equilibrium concentration is going to be 0.274, that was the initial amount, plus any extra we get from the silver iodide. Now, the nice news is most of the time, as we could with previous ice tables, we can neglect X because the KSP values are so small. So look at that, 10 to the minus 17. That means almost none of, that means the amount of this X that's going to form is negligible compared to the 0.274. So that simplifies our math quite a bit. All right, so looking at our math, we were given the KSP value for silver iodide. We're plugging in our equilibrium concentrations of the ions. We're going to neglect X. And then we simplify solve for X, that is 3.11 times 10 to the minus 16. And incidentally, the solubility of silver iodide in pure water, that means water when you have not dumped a common ion in, like sodium iodide, is 9.23 times 10 to the minus 9. So check this out. That little bit of sodium iodide, well, not really little, well, 0.274 is not really little, but that amount of sodium iodide we dumped in water has decreased the solubility of silver iodide by 7 orders of magnitude. That is more than 1,000,000 times. Here is the last topic in the KSP lecture, and it's will a precipitation occur? Will a precipitate form? And again, I think I've just decided during this lecture that one of my bonus questions is either going to be this type of problem, will a precipitate form, or a common ion problem. They do show up on the ACS final, and I think most people probably don't have time to address it. But for those of you super achievers that maybe want to get a super duper high ACS final score, it'll really behoove you to know how to work these two types of problems. All right, so if you're given a problem that gives you two different ionic compounds and essentially mixes them together and says, will a precipitate form? Really what you want to think about is a double replacement reaction. That's really what's going on. If you remember that from first semester of chemistry, we mix two ionic compounds and they switch partners. And so if they swapped partners, what would the two products be? Well, the silver would end up with the chromate, and the sodium would end up with the nitrate. So in order to answer this type of problem, you need to remember solubility rules, which further complicates this. So again, I'm hoping you remember that anything with a sodium metal in it is soluble. Anything from a group 1 metal. So that's completely soluble. So there's no way that would form a precipitate. Remember the definition of precipitate. It's an insoluble solid, okay? So this, as a matter of fact, would form a precipitate, a solid. It's insoluble, relatively insoluble. Another way to discover what the precipitate would be to simply dissolve each of the two ionic compounds given. In other words, break them apart, dissociate them into the cations and anions, and ask yourself which combination of two ions from this pool would give you something that's insoluble. And if this is an easier approach to you than actually doing the double replacement, that's fine, but you should end up with the same knowledge that silver chromate would form in a precipitate. Once you have identified what the precipitate could be, you want to write up an equilibrium expression for that insoluble salt, because it's always the equilibrium that allows you to set up a KSP value and an ice table. So notice that you have to know your charges, and so that's why this is clearly an A-level problem. So there's your KSP, or your chemical equation. Your KSP expression would be concentration of the silver ion squared times concentration of the chromate ion. Alrighty, and what this question didn't provide, which it should have, is the actual KSP value for silver chromate. And actually, whatever KSP value they give you, that they're essentially telling you what the precipitate would be. All right, so I should have given this in the problem, but KSP is 1.1 times 10 to the minus 12. So normally they would have, like as an aside, KSP for silver chromate is 1.1 times 10 to the minus 12. And so you would look for that and say, oh, silver chromate is the precipitate, and then you could proceed to write the dissolution equilibrium. Alrighty, so moving on to how we would set up the ice table. Again, here's the equilibrium that we're dealing with for silver chromate. Make sure you've got your stoichiometry correct. And so what you're going to do in this type of problem, when you're mixing two ionic compounds together, you're going to calculate a Q value. So remember, Q is the same math as K. In other words, concentration of the silver ion squared times concentration of the chromate ion. And you're going to plug in these concentration values as they were given in the problem, calculate what Q would be, and then see if Q, how it compares to K. Okay, if the current concentration product, Q, is greater than K, that means it's got to decrease. That means you're going to see a precipitate, okay, if Q is greater than K. If Q, the current concentration product, is less than K, that means you're fine. They're going to stay dissolved. You're not going to see a precipitate form. So here are the amounts the problem gave us. The concentration of silver, 1.5 times 10 to the minus 4. If you want to go back to the problem, that was concentration of silver nitrate. And since silver is in a 1-to-1 ratio with silver nitrate, its concentration is going to be the same. The concentration of chromate is, they just gave us a gram, a mass amount that they dumped in, and it was 1 times 10 to the minus 3 grams. So we have to get that in terms of concentration. So first we have to convert the grams to moles. We divide by the molar mass. We divide by the molar mass of the entire ionic compound that was added, okay? So it wasn't just chromate that was added, it was added in the form of sodium chromate. So this is sodium chromate's molar mass. That tells us how many moles of sodium chromate we've added. And then the volume of the solution is 0.225 liters, which tells us the molarity of the chromate ion. So if we go back to the expression for Q or K and plug in these values, here they are. Don't forget to square the silver concentration. We get a Q value equal to 6.2 times 10 to the minus 13. Now we need to compare that to K. Okay, what is the relationship? Q is less than K. Okay, there's more negative exponent. Q is less than K, which means it'll stay dissolved. There's no problem. We haven't reached a saturation point yet, so no precipitation will occur.